Thank you. Thank you very much. So it's really great pleasure to be here with you. So it's already my third time in Nepal, and I think the fourth time I'm participating in this school. So I was also once during COVID online, and I hope you can see the slides. Yeah. So I used to joke saying that I have the best job in the world. So the DeepMind chair at Oxford. So it gives me this opportunity to harass Google at every machine learning conference, asking them to show me my chair. So I already do it more or less every time. So some of them even recognize me there at the Google booth. So when we gave last year, we gave the honorary PhD to Demis Hassabis, the CEO of DeepMind. So we made him sit on the what he described as the most uncomfortable chair in his life. So we obviously Oxford has ways to pay back in a subtle way. But I would like to say maybe a few words about this event. So I think it's been really a great experience. So I participated. I think it was either the first or the second one. The second, but it was in Pokhara, not in Kathmandu. So was my first experience in Nepal, and last year was also great. So I was here with 3 of my PhD students, and we had also amazing experience. And if I guess many of you are locals, so I think these are wonderful places as well to explore. And this year also 2 of my PhD students and a colleague from Vienna, Ismail, will be presenting part of this class. So basically, it's a pared down version of the geometric deep learning class that I teach at Oxford. So the broad topic of what we are going to talk about in these 2 days, and probably in general in these 10 days of this school, is artificial intelligence, right? And it's a kind of thing that is a little bit amorphous, right? So nobody really knows what artificial intelligence is, right? So everybody likes to use it, so it has become a kind of almost business buzzword, but if you ask for a definition, probably everybody will come up with a different definition, and it's been a kind of a moving target, right? So since the term appeared in the 50s, it was somehow to imitate what humans are capable of doing, but somehow we don't really know how to quantify, right? And you can find at least some things that are considered to be hallmarks of human intelligence, which is world perception, right? So visual perception in particular, the faculty of language, playing intelligent games, and some sort of creativity, right? Arts, you can call it. And since then, we made great progress in all of these, right? So I would say that perception, we already probably have it solved, right? So we have autonomous driving cars. About language faculty, right? So we nowadays can translate languages without a dictionary, right? So, and if you look at the way that we can deal with language, it's probably more or less done, right? So something that has been almost science fiction a few years ago now is more or less everyday reality. Playing intelligent games, right? So in the late 90s, so chess surrendered to a computer, and then about 10 years ago, the more complicated game of Go, right? And nowadays, computers can play games infinitely better than humans. In terms of creativity, we have now also something that might have looked like science fiction just a few years ago. So nowadays, AI-generated images even win artistic competitions, and yet we cannot say that we have artificial intelligence. Right, so it's probably in the eyes of the beholder. So we would probably like to stick to more mathematically defined terms. So in this very broad field of what is often called artificial intelligence, there is a subfield that is called machine learning, and in particular, we'll be talking about deep learning that is implemented using deep neural networks, right? And this is well defined, and we'll be talking about some of the foundations of this topic. So there was this famous quote from Andrew Ng from 2017. So he was saying that machine learning is the new electricity, in the sense that it is a transformative technology that drives the new industrial revolution. And there was also, from the same year, there was Ali Rahimi was given the best paper award at NeurIPS. It was still called NIPS at that time, so one of the main ML conferences. And he was talking maybe a little bit bitterly about the overall spirit of machine learning community, that there is this self-congratulatory feeling in the air. We say things like machine learning is the new electricity. I'd like to offer an alternative metaphor. Machine learning has become alchemy. So he was complaining about the lack of understanding what actually deep learning does, right? So neural networks, black boxes, not clear what they are doing. So I think the situation is maybe slightly different from now from maybe at that time, but still probably there is much truth in it. So what we will be trying to offer is what we call geometric deep learning. So it will be basically studying fundamental principles that underlie deep learning architectures, and we would like to offer a perspective, again, geometric perspective, but it will be some sort of guiding principle that hopefully will make the black boxes slightly more understandable. And here I would like to use another quote. So this is from Helvetius, a famous Swiss philosopher. So he was saying that the knowledge of principles compensates for the lack of knowledge of facts. And this is the mindset and the spirit I would like you to have in these days, is to, once you understand the principles, you can derive everything from these principles, right? So we would like the field is moving very fast, so principles usually persist for longer than particular architectures or particular implementations. So one of the important principles that we will be using is the notion of symmetry. And symmetry is a mathematical concept, and Weil, who was a famous German mathematician, was poetically talking about symmetry about 100 years ago, saying that as wide or as narrow as you may define its meaning, it's one idea by which man through the ages has tried to comprehend and create order, beauty, and perfection. So this will be the foundation, you will see how, for more or less everything that exists in the field of deep learning. Okay? So symmetry itself goes back to the ancient Greeks. In fact, it's a Greek term, and the Greeks believed that everything in the world has to do with symmetry. So Plato, more than 2,000 years ago, believed that all the world around us is composed of tiny symmetric polyhedra that we call nowadays Platonic solids. So if you think of it, it's not such a crazy idea, because we now understand that crystals are organized this way, right? And actually the first one to try to mathematically model crystals was Johann Kepler. So he's a famous German astronomer. So he wrote these treatise in about 500 years ago, trying to understand how the crystals of water, ice crystals or snowflakes are composed, right? So that was famous packing problems. But Greeks are also credited with formalizing the geometry for the first time. So this is something that we still teach as the geometry at school, and this is the Euclidean geometry. As you probably know, the Euclidean geometry is based on 5 axioms or postulates, the fifth of which, about parallel lines, somehow stands out. And for many centuries, if not more than 1,000 years, a line of illustrious mathematicians try to do something with it, to prove or disprove it, to no avail, right? So it somehow evaded even the best mathematicians until the beginning of the 19th century, where came for the first time the realization that you can actually construct self-consistent versions of geometry without resorting to the postulate of parallel lines of the Euclidean geometry, right? And again, there was a line of famous mathematicians. So Gauss himself apparently worked on non-Euclidean geometry, but never dared to publish. The first one to publish was Lobachevsky, so it was he was subjected to a lot of ridicule, because it was very considered initially a very heretic idea that how dare you challenge Euclid that stood for more than 2,000 years. But then towards the end of, or the second half of the 19th century, these ideas became more accepted, and multiple different geometries evolved in the community. So it required a different mindset or a different approach to even understand what defines a geometry. And this new insight came from Felix Klein. So he was very young, 23 years old, German mathematician. He was offered a professorship at the University of Erlangen in Germany, and as it was customary, he was asked to present an inaugural lecture where he would be basically would be presenting his research. So it entered the history of mathematics as the Erlangen program, in which he proposed a radically new idea of how to define geometry, basically considering properties that remain invariant and when you subject geometric shapes by some transformations. So if you look at, for example, Euclidean transformations, right? So this is what defines the classical Euclidean geometry. Basically, all the properties that are unaffected by rigid motions, rotations, reflections, and translations. They preserve volumes, they preserve parallelism, they preserve intersections, they preserve angles, you name it, right? And you can choose a different class of transformations. We'll formalize it using the language of group theory. So basically, you can derive different geometries by just choosing a different group. So this was a radically new idea in geometry. You can argue that it was the second time that geometry was algebraized. So the first one was done by Descartes with the idea of coordinates. And it had profound impact on mathematics culturally, but also on physics. So in the beginning of the 20th century came for the first time the realization that in physics, like in mathematics, you can also derive from fundamental laws of physics, fundamental laws of universe, like conservation laws, from these first principle considerations. So for example, Emmy Noether proved that conservation laws can be like conservation of energy, that before that was empirical, could be derived from, for example, symmetry of time, right? So that was really a radically new idea, and it shaped our understanding of physics, and all modern physics can be traced back to these ideas. So physicists like to talk about external symmetries of space-time and internal symmetries of quantum fields. So what we know as the standard model, so this is our best understanding of physics that holds water since the 70s, goes back to all these foundational principles, right? And Philip Anderson, Nobel laureate in physics, laconically said that it's only slightly overstating to say that physics is the study of symmetry, right? So everything is symmetry to some extent. Now you can ask, what does it have to do with machine learning, right? And deep learning and artificial intelligence. So you will hopefully see the relation, but let me maybe take you back to the history of the field, right? So artificial intelligence is actually a pretty recent field if you compare it to other sciences, right, or engineering disciplines. The name itself goes back to the famous Dartmouth Conference. So in 1956, a bunch of young researchers, many of them became professors at MIT and a few other American institutions, gathered Dartmouth College, so one of the Ivy League universities in the US, and they wanted to basically to solve the problem of intelligence in over the summer, right? That was very ambitious and obviously unachievable goal. So you can probably recognize some of the names here. So Marvin Minsky, John McCarthy, Claude Shannon, right, the father of the information theory. So some of them are young and active and can be seen in this picture. So around that time also appeared the first neural networks. So in 1957, Frank Rosenblatt, who was funded by the US military agencies, developed the first neural networks that he called perceptrons, and also learning rules. So basically it was a mathematical abstraction of the brain, right? I should say very different from the way that the brain works and the brain learns. But it was received with a lot of enthusiasm because he was able to show actually solving some practical problems with these architectures. And I should say that even though he's credited mostly with perceptrons, actually his work was more general. Many of the things that are considered the hallmarks of modern deep learning go back to some of his works, like, for example, skip connections. And of course, it came with a lot of early hype. So this was an article in the New Yorker from '57. So perceptrons, right? And we're talking about just single layer, very simple neural networks. So the New Yorker proclaimed that the first serious rival to the human brain, or remarkable machine that is capable of what amounts to thought, right? So it's pretty amazing how hyped it was. So I should say that I usually give an analogy to modern AI hype, but I probably should be not making this analogy because I think the progress that we've been seeing in the last couple of years is remarkable. So I wouldn't be downplaying it. So I think now it looks very different. So also early examples of early hype. So this is from the 60s. So it was Seymour paper. So the MIT Summer Vision project. So they, for the first time, could connect a camera to the computer. So they wanted to solve the computer vision problem over the summer. So it was a graduate student project. And of course, computer vision is an active field, and we don't have it solved yet. So Papert is also one of the authors of this famous or infamous book called The Perceptrons. So it was basically a criticism of the early neural networks, and it is probably mostly famous for the XOR affair, right? So it's mathematical proof showing that perceptrons are unable to solve very simple problems, right? So in this case, they cannot represent the exclusive OR logical function, right? So in technical terms, you can say that this sort of problem is not linearly separable, and it's usually credited by AI historians for the first AI winter. So this is not correct. Actually, there are other reasons why the first AI winter, or why the neural networks, the first neural networks fell out of favor. First of all, I should say that maybe on the technical side of the book, so many people who quote it never read it. You can actually find it online. So what they called perceptron and what Rosenblatt called perceptron is a very different thing. So basically, they use the term for a simple mathematical architecture that is inspired by the work of Rosenblatt. So it's a single layer neural network with sign activation. But probably the overlooked part of this book is it was the first geometric approach to machine learning problems, at least to the best of my knowledge. And actually the subtitle to the book was An Introduction to Computational Geometry, with computational geometry being a new term. So they invented it. It was, I remind you, it was 1969. Now, of course, you have journals and conferences on computational geometry, but at that time it was not even clear whether this will be just, again, some kind of hype that was invented by two guys from MIT, or it will become a real field. So in the book, they introduce some of the first geometric takes, including based on group theory. So this is something that we'll be discussing on machine learning problems. They are mainly interested in impossibility results. In fact, the cover of the book shows examples of parity. So one of these figures is connected, another one is not, right? And it's even difficult for a human to determine it. So they wanted to be able to show that some problems are impossible to solve using geometric considerations. Okay. Now, so this notion that neural networks cannot represent certain things is important. In fact, you can go back with these mathematical results all the way to David Hilbert. So one of his famous problems, in particular the 13th problem in a certain formulation, has to do with what we call universal approximation results. So in the 50s, there was already a version of universal approximation result that was not particular for neural networks, but it was proven by Kolmogorov and Arnold. And actually, there is a class of neural network architecture that is called Kolmogorov-Arnold neural networks. So basically, some modern incarnation of these results from the 80s and from the 90s is what nowadays is called universal approximation results. Basically, it's this notion that if you connect two layers of a perceptron, right, like Rosenblatt did in some of his works, all these concerns about not being able to represent even simple logical functions are put to rest. So you can represent anything, right? I will show the exact formulation of one of the universal approximation theorems. Basically, it tells you that roughly any continuous functions can be approximated to any desired accuracy, right? So this is what neural networks are basically powerful, and they can do more or less anything you want, right? So if you look at it from this perspective, if you look at supervised machine learning problems, so think of your neural network as some sort of a black box, right? And let's say that you want to classify dogs and cats, right? So very simple image classification task, right? So I input cats and dogs into some neural network. I want to produce as an output a binary label, right? So whether it's a cat or a dog, right? So we know that you can do it, right? So basically any complicated classification function, right, due to a universal approximation property can be represented. But of course, the question that you want to ask is, how to do it, right? So the first question you will be asking, for example, is how many samples do you need, right? So if I give you certain accuracy threshold, for example, let's call it epsilon, how many samples do I need, right? So how many examples of cats and dogs do I need? So this is a very practical question, right? So how big my training set should be. So first of all, when we talk about continuous functions, it's too broad a class, right? So we have infinitely many crazy continuous functions, right? So being continuous is too weak a property. So we need something, some stronger notion of regularity, right? So, and the mathematicians, of course, have good notions of regularity, so we can take very well-behaved functions like Lipschitz continuous function. Again, we'll talk about specific definitions, what it means, and we can quantify the number of samples that we need to take of this function in certain number of dimensions in order to get this approximation error epsilon, right? The problem is that everything behaves nicely in one dimension, in two dimensions, but as we start growing the dimensionality, we get to the problem that the number of samples grows exponentially with the dimension, right? So it's 1 over epsilon to the power d, right? And for any practical machine learning problem, right, especially in problems that like image recognition where the dimensionality is in the thousands or in the millions, you will need more samples than the entire population, not only the entire population of cats and dogs on Earth, more than the number of atoms in the universe, more than anything else, right? So it's exponentially large number, and basically this problem of exponential growth of the number of samples was already recognized in the 70s, so that was this famous Lighthill report that was also credited for the initial demise of the neural network approaches. So we need some other ways of dealing with this curse of dimensionality, and in the neural network architecture world, it came actually from the works in neuroscience. So this was probably one of the first and only cases, again, to my knowledge, where neuroscience was useful, at least in some way, for informing deep neural network architectures. And it came from two neuroscientists, Hubel and Wiesel, working at Harvard. So they were studying the connectivity and the function of the visual cortex of mammals. In particular, they were working with cats. And as many important discoveries, it was completely by chance. So there are, you can see this is from their experiments. So they were showing different patterns to the cat, and had electrodes planted in the cat's brain to see the response of the neurons, and different patterns failed to produce the response that they were hoping. But they noticed that the moment that they were putting the slide into the projector, and I remind you it was in the 60s, so the projectors were literally the transparencies, right? So where you basically a lamp and a transparency. So when you put the transparency inside the projector, the border, the boundary of the transparency, you can see it here, this kind of straight line was the one that was producing interesting responses in the cat's brain. So they were looking at it, trying to understand this surprising phenomenon, and they came up with a discovery that gave them the Nobel Prize in Medicine in 1981. So that was basically direction and position dependent responses. So in the computer science world, first Kunihiko Fukushima tried to imitate these findings in a neural network architecture that he called the neocognitron. So it basically, if you read the paper, it even uses the neuroscience terminology. So it was basically a computer model of the Hubel and Wiesel findings. So it had simple cell and complex cells that were organized in hierarchically. And one of the reasons why he wanted to do it was for optical character recognition. So in the 60s, it was an important problem to basically to scan texts and written text and convert them into something that they could be machine intelligible. And he was particularly criticizing perceptrons for the lack of translation invariance. So it was, neocognitron was a very modern architecture by today's standards. So it was a deep neural network with 7 layers. It had local connectivity, what is called receptive fields. It had nonlinear filters, average pooling, and even ReLU activations. So Fukushima was using ReLUs already in the 60s. So it's not something that is is a feature of modern architecture. It was already pretty old and exists for quite some time. What he didn't have was backpropagation. So backpropagation already existed, but it was not commonly used until the mid-80s. And basically, since the famous work of Rumelhart and Hinton, it became popular in the world of deep neural networks. Now, in the late 80s, Jan LeCun, who started his postdoc at Bell Labs in New Jersey. So at that time, Bell Labs was it was the deep mind of in the computer science world, as nowadays DeepMind is, right? So it was the coolest place to be. So they were also manufacturing their own digital signal processors. So the DSPs were the GPUs of that time. So basically, he took Fukushima's architecture and removed all the neuroscience terminology, removed all the nonlinearities, made it compatible with the hardware. And these were convolutional neural networks. Actually, the term convolutional appeared in later publications. And he was able to, in this way, so also training the neural network by propagation, was able to solve practical problems. So you have probably seen this video. So this is a young version of LeCun in the 90s showing handwritten digit recognition. So it was a commercial product that AT&T was using for handwritten digit recognition. So it was, for example, reading bank checks and was deployed in multiple financial institutions. So basically, if you look at these questions, right? So how to recognize objects, right? And if you look at this of this example, whether it's a cat or a dog, so it sounds like a silly question. Of course, we know that this is a cat, right? So even the 2-year-old child can probably solve this question, but it is very difficult to solve this question on a computer, right? So because we don't have really a mathematical model of a cat, right? We don't have an equation of a cat. So we can, of course, try to come up with an equation of a cat, and the computer vision community did it for many years, trying to come up with handcrafted descriptors telling what makes a cat look like a cat. The alternative approach is to say somehow when you see a cat, you know it's a cat, right? So just give me thousands of or millions of examples of cats and not cats, and somehow learn from these examples what they are, right? So the computer vision community probably in the last 20 years or so was trying to do the equation of the cat, right? So this is a typical image recognition pipeline from the early 2000s, right? So this was from a colleague at Oxford, Andrew Zisserman, so one of the most cited papers, detect some regions in images, describe them in some way, then build histograms of these features and try to recognize images in this way. So what happened in 2012 was convergence of 3 trends. So it was, first of all, the growing computational power, in particular GPUs that initially were designed for applications in computer graphics, but then became useful for general purpose computing. Available data sets, so this gargantuan effort that was led by Fei-Fei Li at Stanford, so annotating manually thousands of different image classes, more than 1.5 million images. That was the ImageNet. And of course, some changes in the architecture. So basically how to make more efficient architectures. So all these culminated in 2012 with the famous AlexNet. So that was a convolutional neural network trained on a pair of GPUs for, I think, almost 2 weeks that was able to solve the large-scale image classification benchmark called ImageNet significantly better than all the handcrafted methods. So if you think of it from the philosophical perspective, the very basic premise of any computational science or any computational modeling, right, or classical software is that you know a priori your logic, right, that you're trying to put in the computer, right? So you have an equation that you're trying to simulate, right, or you have that you can write in software, run on the computer on some set of data, and then you produce the desired behavior, right? So this is how we simulate weather. This is how we simulate drugs. This is how we tried to classify cats, right? But we don't have an equation of a cat, right? Or we don't have an equation of a cell, right? So if you think of complicated, especially biological problems, you don't know where to start, right? So you don't have the logic to start with. So deep learning inverts these paradigms. So you don't start with the logic that you put in a computer. You start with the data. You start with examples of data. So this is your training data, and then you figure out the software implicitly in the form of weights of a neural network, right? So this is what Andrei Karpathy called software 2.0, and it was significantly better than anything that you can handcraft, because often you start with something that is a better approximation of your problem, or you don't have even a good model at all, right? So if you have a good model, maybe you should use the software 1 paradigm, but in many cases you don't, so you have no choice to use machine learning, right? And the rest, of course, is history. So Turing Award was given in 2018 for deep learning, and it created a multi-billion industry. So the rest is history. Now, let me just finish with maybe a few other historical remarks. And I would like in particular to talk about graph neural networks. So this will be an important topic in our discussion, especially today and a little bit tomorrow. And actually some of the origins of graph neural networks are from chemistry. So as you probably know, chemistry is one of the fields that historically has been very data intensive. So when chemists discover new compounds or do new chemical reactions, so they record them, and it basically very quickly grew into gigantic troves of data. So a new compound, a new molecule, a new chemical reaction, all had to be recorded in some way. So there are these books with hundreds, if not thousands, of volumes documenting all of these. The first chemical journals that were trying to do it. So in the beginning of the 20th century, it became clear that if you want to make it manageable, try to make it an automated service. So this is where the CAS of the American Chemical Society appeared, and also first attempts to search in these data sets, right? Imagine that you patent a new drug and you want to see whether somebody has invented it before, right? Whether it's known to science. So you need to look up it in the data set of hundreds of millions of molecules, right? Whether something like this is known. So the first attempts in chemoinformatics were actually these kind of punch cards, right? So this is even before the first digital computers appeared. So mechanical system for retrieval of chemical compounds. So you need to be able to take a molecule, right, which is a geometric object, and represent it in a way that you can search on a computer in the form of a string. So one of the pioneers of this field that later was given the name of chemoinformatics was Georg Vladots. So he was a Romanian working in Moscow, and he came up with the idea of treating molecules as graphs. So you represent the molecule as a graph. Why? Because when chemists think of molecules, they don't think of just collection of atoms and chemical bonds. They think of structures, right? And structure is something that is very natural to describe as a graph. So he was trying to describe chemical compounds in this way. I should also say that the term graph itself, actually, it was introduced by John Sylvester, a British mathematician, that was referring to the early structural chemical formula. So he used the term graph or chemical graph, even though the graphs existed probably since the time of Euler. At least he's credited with the invention of graph theory. At least the term itself goes back to Sylvester, and it was inspired by chemistry. So one of the algorithms that we'll be talking about today, which is Weisfeier-Lehmann graph isomorphism test, so its fundamental result in graph theory, was also inspired by chemistry. Actually, in this famous paper, they credit Vladots for posing the problem. So basically, he came to them asking, can you solve the graph isomorphism problem in order to help me search molecules? So first graph neural networks appeared already in the 90s, even though, again, their precursors go back without maybe any learning to the 60s, to the problems in chemistry, molecular fingerprints, but they became popular in the neural network community thanks to these works that I cite here. And they were brought back more recently, about 2017, again in the chemical problems. So basically, can you compute molecular fingerprints faster and more accurately? So I should also say that the biochemistry community has had its own ImageNet moment. So, and I'm talking about the AlphaFold. So that was also a holy grail difficult problem in structural biology, predicting the three-dimensional folding patterns of protein molecules. Well, I will talk about it probably in the last lecture. And there was a competition that was running similar to ImageNet, where structural biologists were trying to compete among each other who predicts better the structure of proteins unknown previously to science. And suddenly everybody was outperformed by an entry from a group that has never been working on protein before, some company called DeepMind, right? So if you has ever heard of them. And basically it was AlphaFold, and the rest is history. So the Nobel Prize in Chemistry was given for Hassabis and Jumper for the development of AlphaFold last year. So basically, if we summarize, right, we have these two examples, right? So we had historical example of convolutional neural networks, and we also had an historical example of graph neural networks, right? So if you look at these, there is nothing similar between them, right? So one deals with images, another one deals with molecules, and yet you can see that in both cases there are some kind of common traits, right? Or common there is a common denominator. So in both cases we have some underlying domain, right? So our data, whether it's images or molecules, they live on some geometric domain, right? So it's a grid in the graph. In both cases we have some sort of symmetry, right? Or what we'll call symmetry. So some sort of transformation that makes sense. So in images, I can move images around, right? So, and I want to be able to say that whether it's the same digit in a different position, I still want to recognize it in the same way. In case of molecules, we can talk about permutations, right? So this is the symmetry that reorders the atoms in a molecule, and still it's the same molecule, it's just represented in a different way, right? In both cases, we have some kind of operation that respects this symmetry. So this is the convolution. We'll talk tomorrow about how to actually derive convolution from these first principles. In the case of graph neural networks, as we'll see, this will be the operation that we call message passing, right? And basically these are you can recognize some traits that will be just instances of a common blueprint that we call the geometric deep learning. So we popularized this term in a paper from 2017 when this field was in its instance, and we like to think of it as some sort of Erlangen program of machine learning. So of course not comparing ourselves to the great Felix Klein, but at least taking some of the philosophical principles from the Erlangen program that he proposed for geometry, right? And basically these zoo of different architectures, whether it's CNNs, GNNs, RNNs, transformers, deep sets, you will see that they all boil down to these instances of this general blueprint. So in the geometric deep learning blueprint, we have a domain on which you can act with a symmetry group. Then if you have data that lives on this domain, you can act on the data as well, right? So through what is called the group representation. And then you can define functions that take this data as input. And these functions are designed in a way that would respect this symmetry, right? In particular, we'll be talking about properties that we call invariance and equivariance. So the classical example are convolutional neural networks, right? So convolutional neural networks, the domain is a grid. The group that is associated with the grid is a translation, right? So it acts on images through the translation operator, and then you can argue that convolution is the only linear operation that commutes with the translation operator. On a graph, you can do the same thing. So the symmetry here is permutation of the nodes of the graph, right? And message passing is an operation that is equivariant with respect to these transformations. You can also come up with a more interesting example. So we'll not be talking about it, but this is what is very popular nowadays in chemistry, including in AlphaFold, right? So equivariant or a geometric graph neural network. So you can have both the symmetry of the domain and the data, and you have special type of message passing that is equivariant with respect to both. So same way as we have these internal and external symmetries in physics, you can have external and internal symmetries in your domain and your data, right? So in particular in molecules, these are geometric graphs, right? So we have both permutation of the atoms, right? So this is the domain symmetry, and transformations of the coordinates of the atoms, which is a continuous symmetry, right? In particular, people look at rotations and translations, right? And basically neural networks can be constructed by just a sequence of equivariant and invariant layers. You can also interleave them with some pooling operations. So we'll mostly be talking about the invariance and equivariance and less about pooling. And again, you can apply this principle to a lot of different things. So anything that looks like a grid or a graph, or more complicated objects like topological spaces, simplicial complexes, cell complexes, manifolds. So the same principles can be applied. So basically it's a general recipe. I give you a problem with its invariance, data that lives on a certain domain. You can derive a special type of architecture that deals with this data, and not surprisingly, basically more or less anything that exists in this field can be constructed from first principles of symmetry, right? So all the popular architectures, whether it's transformers, GNNs, CNNs, RNNs, you name it. And of course, in many cases, the symmetry actually comes from the problem itself. So this is especially true in natural sciences, in physics, in biology. So that's why these architectures have become very popular in different applications of AI for science. And there is, of course, also a lot of commercial interest. So there are multiple companies, especially in the biotech field, that basically use these kind of methods and this kind of technology for developing new products, in particular designing new molecules and new drugs. There are maybe some more exotic applications, like so this is my collaborator from DeepMind. So they were using graph neural networks to predict how football players will be performing in different games. So they cooperated with, don't ask me, I don't remember which famous football club in the UK, but yeah, so apparently there are even applications like this. So that's it about the introduction. So maybe just a few words about the logistics. So I guess you could see the schedule. So we'll be talking today about, so this is the schedule for today. So after the introduction, unless you have any questions, we will be talking about basics of machine learning. So here the emphasis will be on learning in high dimensions. So we'll see that many things that are taken for granted in low dimensions become suddenly problematic in high dimensional spaces. So this will lead us to the notion of regularity, and we'll be talking about geometric priors, in particular based on group theory, symmetry and invariance. So this will be the first lecture after the break. Then we'll be talking about deep learning on sets. So how to design architectures where your object is a set. So this is probably the basic and the crudest geometric object, right? So basically just a collection of things, right? Then we'll be talking about graphs. So this will be Ismail talking about graph neural networks. So starting with very basic graph neural network architectures and going to more sophisticated things, studying the expressive power of graph neural networks. So this will be related also to universal approximation results on under the permutation invariance, and then some more advanced topics, so including how to deal with knowledge graphs and how to develop foundation models for graph structured data. And that will be for today. And tomorrow we'll be talking about transformers, about grids, talking about convolutional neural networks again from this geometric perspective. So I will show you how to derive the convolution and the Fourier transform from first principles. We'll talk about physics-inspired architectures and basically how you can think of neural networks as discretized differential equations, and then talk about generative models and how they can be used also in this context of geometry. So the references, so there is, so we have a proto book that is called exactly this, Geometric Deep Learning, and also some chapters of the full version of the book. And we also had, so for the previous version of this course, we wrote together with Okaris, a PhD student, the math background. So if you have some lacking of understanding, or if you want to refresh your background in mathematics, so basically all the main concepts are explained in these documents, so you can find it online. And we also have all the slides, of course, of the course are available through the organizers, but we also have a website that is called geometricdeeplearning.com, so there are even a recorded YouTube version of this course, well, from a few years ago, but the principles are more or less the same. So you're welcome to watch it if you want. Good. Any questions so far before I dive into the technical details? No questions? Good. So let's then move to the actual stuff.